All right, another very useful operation is closure. So what is the closure of a relation? It's basically means we have some relation and we want some property that it satisfies, but it doesn't satisfy this property. So we want to enforce some property with the sort of minimum possible change to our relation. So to be precise, what does this mean? The closure of R with respect to some property P. So we'll see a lot of examples, but for now, let's just say an arbitrary property. Is, so first of all, may not exist, but if such a thing exists, then it is a closure, which is the relation S on the same set, such that S has property P, and basically for any other relation that also contains R and has property P, it must contain S. So if R is a subset of T, wait, excuse me. I want to say that S contains R. So it's a relation that contains R and that has property P and that is minimal with respect to those requirements. So if R is contained in another relation T and T has property P, then S is also contained in T. So this is a sort of maneuver that you might see many places, where you encode the fact that something is the minimal choice, or the sort of best choice in this case, by saying that if there's some other thing that also works, then it contains the thing that we are choosing. So this is what is meaning that S is minimal with respect to these requirements. So let me write that down. It is sort of the minimal P relation containing R. So let's see some examples. Let's apply this to some of the important properties we looked at before. So consider R to be the relation given by less than, let's say, on the real numbers. So we saw that R is not reflexive because a number is not less than itself. So what is the reflexive closure of R? And basically, how can we figure this out? Well, it must contain R. That's just one of the basic properties that we require of it. And to be reflexive, it must contain x comma x for any x in the real numbers. And if we just take all of those things together, then that will give us the minimal relation that satisfies both of those properties. In this case, this is the relation less than or equal to, because x is related to y if x is less than y. That's what this is saying. And x is also related to y if x is equal to y. That's what this is saying. So taking the reflexive closure in this case just changes less than to less than or equal to. And reflexive closure in general does basically the same thing. It changes some relation into related or equal to. And one way to formalize this is following. In general, the reflexive closure of R is R union the diagonal. So this is a Greek letter capital delta. For anyone who is not familiar. And what does it mean? It stands for where delta is the diagonal. Which is essentially what we wrote right here. So it's x comma x for any x in real numbers. And it's called the diagonal because if you were to plot this, since it's, so in this case, we're dealing with the real numbers. So it's a subset of R cross R, which is the two-dimensional plane. And if you plot it, it is the diagonal like that. So that's why it's called the diagonal. But you can apply this to any set A. And the reflexive closure is obtained just by taking the union of your relation with the diagonal. And so same example. We know that this is also not symmetric because if x is less than y, then it is not the case that y is less than x. What is the symmetric closure? Well, we can use similar reasoning just by saying that it must contain R, first of all, if it's a closure of R. And furthermore, it must contain the sort of symmetric swap of any element of R. And must contain y comma x for any x comma y in R. So in this case, this is sort of taking x comma y where x is less than y and x comma y where x is greater than y, because that's what you get when you swap the coordinates. And this is just the set of x comma y where x is not equal to y. Saying they are not equal is the same thing as saying that they are either greater or less than. So the symmetric closure of less than is not equal to. And again, we can make a general picture out of this. In general, the symmetric closure is gotten by taking R union R inverse, where R inverse is exactly what we did here, where you just swap the order. So it is pairs x comma y, or let me say it's pairs y comma x, such that x comma y is in R. So to get the symmetric closure, you just take the swap of each of the elements and throw it in. And finally, let's do an example of transitive closure. So the R that we're dealing with now is already transitive. So its transitive closure would be itself. So let's consider something else. Let's consider our example of a non-transitive relation, which is the neighbor relation. Let's say on the integers. What is the transitive closure of this? So let's try to do a similar sort of reasoning, although it might take a little bit more this time, because we might have to apply it more than once. So let's think about some element a comma a plus 1 that's in our relation R. So it has to contain this because this is in R. And transitivity means that we're allowed to chain things together. So a is related to a plus 2, or sorry, a plus 1 is related to a plus 2. So it must also contain, so let's write a list of things it must contain. It must also contain a comma a plus 2, because that's what we get when we apply transitivity to this and this, which is also in our relation. Well, let me not delete that. Let me say that is how you're getting this element, is by transitivity. And similarly, it must contain a comma a, because that's combining a with a plus 1 and a plus 1 with a the other direction. These things, since we got them by combining one element in this relation and another element in this relation, they are in the second power of this relation. Okay, and if we continue this process, we can subtract another one, a minus 1, and we can add another one on this side, a plus 3. These are in the cube of our relation, and so on, etc., etc. If you continue this process, you'll see that you must get every pair, because starting from any number a, you can get a comma a minus any number, or a comma a plus any number. And that's everything. So the transitive closure is the trivial relation z cross z. And in general, writing things down this side is exactly how you get the transitive closure in general. So the transitive closure is given by taking the union of all the powers of your relation. And just as a quick note, if your set that you're taking this relation on has finitely many elements, then you don't need to take an infinite union. You can just take up to the number of elements. But in general, if you have an infinite set, for example, in this case that we just did, that is very much the case, you do need to take the infinite union of all powers of your relation, and it will give you the transitive closure.